Welcome, everybody. And today I'll be talking about hierarchical approach for automated ICD-10 coding using phrase level attention. First, a little bit about myself. My name is Cansu Shen, and I'm a senior machine learning and AI scientist at Codametrics. I hold a PhD in computer science, and I have been doing machine learning and NLP research for the past 8-ish year. At Codametrics, we use AI to translate medical histories into automated reimbursement. We use digital patient records and, more specifically, clinical notes. And with machine learning and NLP, we predict ICD, CPT, and modifier codes for automating the medical billing process. Today, I'll be talking about ICD Prediction Task. So let me first give you a brief background about ICDs and ICD prediction. ICD stands for International Classification of Diseases, and it's a medical classification list generated by the World Health Organization. ICD codes have various different uses, ranging from billing to predictive modeling of anything about patient state. Since manual coding is time-consuming and error-prone, predicting ICD codes using machine learning methods has gained a lot of interest recently, both from the academia and industry. And it's a challenging task for a number of reasons. First of all, we have a very high-dimensional label space. Right now, there are more than 70,000 ICD codes. Second of all, not every medical event is relevant to the encounter. So, for example, if a lung nodule is detected during a follow-up chest CT imaging procedure, it's a codable event. But if it was detected incidentally during a chest X-ray performed for a fracture diagnosis, then it's not codable. And this adds an extra level of challenge. And finally, if we're building these models to use in the wild, then interpretability is a very crucial part of the machine learning models we're training. As I mentioned in the previous slide, there can be many different reasons why we may want to predict ICD codes. So, for example, named entities related to diagnosis codes can be very useful features for a bunch of different downstream medical tasks or medical document understanding overall. And there is a number of tools and libraries available to identify entities in a text that may be related to an ICD code. And these are great value if you want to use this information to input for another downstream task. But if the end goal is to automate the billing process, then the task looks more like this. We typically have a very long clinical report. And most of the time, there is some other accompanying information with this report. So, for example, you may have demographic information about the patient, or you can have other information about the encounter. So, like, you have all this information on the input side. And we try to predict a handful of ICD codes. So this task I'm just describing is a typical example of a multi-label classification problem. On the input side, we have a node or something else, and on the outside, on the label side, so we have a label space, and out of this label space, a subset is the correct label. And for each case, we have a different number of correct labels. And the goal is to map the inputs to outputs. So since this is a common task, there are some academic papers available focusing on the ICD prediction task using these multi-label classification approaches. When we look at these methods, we see a couple of common problems, and one of them is overcoding. Since we have only a few codes for each case, and the label space is very large, we usually see that these methods tend to overcode, meaning they tend to assign more ICD codes than the correct number. If we look at the top 10 or top 20 codes predicted by these methods, the correct ICD code set is usually within these top 10 or top 20 codes. But these kind of approximate ways of evaluating the model is not quite useful if we're interested in using these algorithms for automation. We're more interested in set predictions and creating more accurate set predictions. Another common problem is that these models tend to pick a part of the input node and only use it for generating the predictions. And they do this for simplifying the problem. So this long input size we see in a clinical node usually creates the problem. So here I'm going to describe another approach, a new approach, by breaking the task down into multiple pieces and turning them around a little bit. So we put together this architecture where we have two standalone models. We have a first level model, which takes all of the sentences from a clinical report and identifies the ones that contain a clinical event or concept that is relevant to ICD coding. So the goal here is to look at each sentence individually and decide if it's relevant or not relevant. So this is a binary classification problem. And at the second level, we have another model. And the purpose of this second level model is to look at only the relevant sentences and assign an ICD code, a single ICD code, to each of these relevant sentences. So this is a multi-class classification problem. And finally, we took these two models and create an end-to-end pipeline by stacking these two models hierarchically to generate a final code set for the entire node. Now, we're going to add another piece to this model. So let's go back to that multi-label classification setting for a while. Our input was a clinical node, and the output is a set of ICD codes. And these two things are the only information we're letting our model to see, and the model learns from this data in an implicit way. So what do I mean by this? I mean that we never tell model which pieces of information is relevant for predicting each single ICD code. The model learns this by itself. Here, we're trying something else. We collect some data to explicitly tell the model relevant parts in a node when making each ICD prediction. And we use this explicit information in two ways. First, we mark the relevant sentences for the first model. And second, we further tell the model which words or phrases are important when making an ICD classification decision. So how did we collect this information? We did a large-scale data collection where we put together a bunch of pathology reports, and we asked coders to read these reports and then look at the assigned ICD codes for that report. First, evaluate if that assignment is correct. If not, just tell us. And then also tell us which pieces of information led to the assignment of that particular ICD code. Here, we're looking at an example report. Like this is a part from an example report. And for this node, the assigned ICD code is Z01.84, which is encounter for antibody response examination. So our coders, our human coder, reads this node and tell us that this ICD code is assigned to this node because of this phrase in this sentence. So this is the information we're collecting here. And if there are multiple ICD codes assigned to that report, we ask our coders to tie each annotation to a specific ICD code. So here, for example, we have this first ICD code assigned to this node, which is C44.519, and it's the code for basal cell carcinoma of skin. So our coder reads this node and let us know that these phrases in the sentence, the basal cell carcinoma and the skin, these are the reasons why this ICD code is assigned to this node. And then they further read the note and see this other sentence here talking about a scar. And they let us know that this phrase triggered the assignment of the second ICD code, which is L90.5. So this slide shows our overall end-to-end architecture. Now this is how it works. The input is a clinical report. And then we first take this clinical report and split it into sentences. Then each sentence is passed to the level 1 model, which is the sentence tagger. The purpose of the sentence tagger is to assign either 0 or 1 to each of these sentences. 0 means this sentence is not important for coding purposes, so just drop it. Don't look at it. And 1 means this sentence is marked as a focus sentence. And if a sentence is marked as a focus sentence, it is passed to our level 2 classifier, which is called the ICD classifier. The ICD classifier takes each focus sentence individually and assigns an ICD code to it. Finally, the predicted code set for the entire case is the union of each assigned ICD code to each focus sentence. Now I'm going to give you a little bit more details about each of these models. First one is the sentence tagger. The core of the sentence tagger is a sequential model. Here we used an LSTM, but you can use any model which can handle sequence-to-sequence classification. So the first thing we do is we generate sentence representations for each of our input sentences. Here we used the mean word embedding to represent our sentences, but again, any other method would be fine as well. If you have some accompanying information, such as reason for visit or a description of the specimen, then you can also generate a vector representation for this information, and you can concatenate that vector representation with your sentence level representations at each step. That's what we're doing here. And finally, these concatenated representations are passed through an LSTM layer, and we assign either 0 or 1 at each step. This is how the sentence tagger works. And our ICD classifier works in the following way. It has 4 different subnetworks. The bottommost network is called the focus sentence encoder. It takes an individual focus sentence, and we first pass the words of these focus sentences through another LSTM, and we generate hidden representations for the words in these in the focus sentences. The next layer we have is an attention layer, but here we use something called a supervised attention mechanism. If you're familiar with attention mechanisms, they've been around for the past 5-ish years, and they usually work in an unsupervised manner. This means that we usually have some input data, and we have a downstream task. We only show model labels for our downstream task. We never tell the model what is important and what is not important. Model generate these attention scores in an unsupervised manner. But we have a different case here. We have some extra information we can use because we're collecting this data from the human coders, and they tell us which specific words or phrases they're paying attention to. So we're using these signals, attention signals, collected from human coders to supervise our attention mechanism. I will tell you a little bit more about this in the coming slides. On top of the attention layer, we have another layer called the classification layer. This is the layer where we use the actual ICD ground truth labels to facilitate learning. And if you have other information, like reason for visit, you can pass it through another subnetwork to encode it. and you can combine that information with your sentence level representations right before the classification layer. Just one more thing I'd like to note here, and that is the attention scores generated by the machine learning algorithms are usually continuous scores between 0 and 1. But the attention signals we're collecting from the human coders, those are binary. And that means human coders either pay attention to a word or they don't. If they're highlighting a word, that means it's a positive signal for us, and we represent that with a 1 value in our attention signal. And otherwise, we use 0. So when we use an attention mechanism, we usually expect to see something like this, something like the attention scores shown in the top figure. We usually assume that the attention mechanism is going to pick just a few very strong signals from the data, and the attention scores for everything else is going to be very similar to it, very close to 0. But that's usually not what happens, especially if we have a very long input. The attention scores most of the time look more similar to what we see in the bottom picture here. So we have a bunch of attention scores. These numbers are usually very close to each other for most of the input data. And if this is the case, it's actually very difficult to use these scores for adding interpretability to your model. By using attention supervision and by using the attention signals we're collecting from our human coders, we're hoping to turn our attention scores more similar to the top picture here, so that we can actually claim interpretability by using this attention mechanism. So our model has ground truth labels at different granularities. The first one is we have sentence level ground truth labels, which are the ICD codes. Using the predicted ICD codes by the model and the ground truth ICD labels we're collecting in our data, we compute a classification loss. We also have some word level ground truth labels, which are the attention signals. So we have the machine attention map, which are the continuous attention scores generated by the machine learning algorithm. And we also have this human attention map, which are coming from the human coders. By comparing these two distributions, we compute another loss, which is called the attention loss. Then the objective function we're using for training our model is the combination of this classification loss and the attention loss. We define a hyperparameter called lambda here to ensure a balance between the classification loss and attention supervision loss. This lambda is a hyperparameter that should be tuned, and you can tune it in a way that to put more attention to either classification or attention supervision. We evaluated our sentence tagger and ICD classifier, and finally the end-to-end pipeline separately. In our dataset, we have roughly 40,000 nodes, and 28,000 of them are used for training purposes, 5,000 of them are used for validation, and another 5,000 are used for testing purposes. So this table here we have on the top, that shows the performance of the sentence tagger on the test set. I want to make 2 points here. First one is, when training our sentence tagger, we have a very imbalanced data set because in each clinical note, we typically have 30 to 40 sentences on average, and only very few of them, like maybe 2 or 3 of them, are focus sentences. This leaves us with a very imbalanced data set. And Of course, we're using some different techniques for tackling this imbalances problem, but this is the main reason why we're seeing a big difference between the micro-average and macro-average I'm showing on that top table. And the second point I'd like to make is about the macro-average precision and recall values. If you look at these two numbers, we have a high difference between them, and we have a high recall and a low precision value. So this was a choice made by us for the following reason. So if a sentence is tagged as a focus sentence by our first level model, we pass that sentence to the next level and we assign an ICD code to that sentence. So if we pass a lot of wrong sentences to the top level, then it's very difficult to recover from that. So we should be able to pass correct sentences to the top level. But if we're passing some additional sentences, and especially if these are very similar sentences to the correct ones, then they're going to get the same ICD prediction assignment. So that's why we wanted to train a high recall model, and that's what we did. So the table we have at the bottom of the page shows the performance of the ICD classifier. So this table it has 5 different columns, and each column shows the performance of a slight variation of the base model. But I'm not going to go into details of each of these model variants. The model I described in the previous slide corresponds to the last column, and that's the one where we get the best performance for the ICD classifier. And finally, this table shows our end-to-end performance. Here, we used a couple of different baselines. Let me briefly explain these baselines as well. The first one is, it comes from a paper which uses classic multi-label classification setting for ICD prediction. And that's actually a very common baseline which is used for ICD Prediction Task. The second and third models I'm showing in this table, they use a technique called binary relevance. So binary relevance models are another way of dealing with multi-label settings. The way they work is they train binary classifiers for each possible label in the label space. So let's say if we have 10,000 different labels, we train 10,000 different classifiers for each of these labels. And then whenever we're going to make a prediction on a data point, we run all of these classifiers, get individual results, and then we combine the results to generate the set prediction. And finally, the last row shows the performance of the model I've been talking about. We see here that the method I've been talking, the proposed method, achieves the best numbers for set accuracy as well as most of the other metrics. I finally want to show one more thing, which is about the effect of supervising the attention mechanism. So here, I'm showing you a text, which is here. And for this text, the assigned ICD code is D22.71. And for this case, our coders highlighted the first 2 words from this sentence. In the case where we didn't use any attention supervision, the scores were more similar to each other. But after the attention score, we see that we were able to get most of the attention scores very close to 0. And the attention scores for the first two words were the highest ones. This shows that we're actually achieving more or a better interpretability with the help of attention supervision. So let me quickly summarize this model and also tell you about the key takeaways. I presented a model for ICD prediction in a way that we use two different models. And by doing this, we were able to turn a multi-label classification into a more simpler binary and multi-class classification tasks. We used phrase-level feedback to ensure learning from human coders and mimicking their approach to coding. This two-step approach I presented is especially suited for service lines where there's fewer number of ICD codes assigned to each case. And pathology is a great example for this. And this is because other methods suffer more from overcoding, and this presented method here suffers less. This model obviously has some limitations, and the most important one of these is we cannot assign more than one ICD code to a single sentence. But this whole architectural design was based on the fact that we see that very rarely in the data. So in our data, very, very small percent of the sentences had more than one ICD codes assigned to it. And if you look at the end-to-end pipeline results that I showed, we actually verify that this model performs better than the other baselines we used. And this shows that this limitation is not creating a bottleneck problem. And finally, we're adding these two levels of interpretability with this approach. So since our sentence tagger operates at the sentence level, we can point at a single sentence as the reason for particular ICD prediction. And finally, with the supervised attention mechanism, we can further identify exact words within a sentence as prediction reasoning. That's all I wanted to say today. Thank you very much for listening, and I'd be happy to answer any questions. Thanks.
What an excellent presentation to end this conference day. A huge thank you to all the speakers for their insightful talks covering state-of-the-art NLP in healthcare and life science. Many thanks to all of you for joining this community event yesterday and today, and for contributing with questions and with your own experience. Over the last 2 days, we have heard more than 30 sessions how NLP is leveraged to improve quality care for patients, the work of medical professionals, as well as how the technology can be applied to accelerate innovation in healthcare and life science. There are so many amazing applications of NLP in this field, and we are excited about everything that is yet to come. If you'd like to catch any of the sessions again or watch those that you have missed today, you can come back here and watch all the content on demand for the next 2 weeks. All the content will be available on this platform shortly and will remain public afterwards. For all of those who would like to dive deeper into applied NLP, we'll also be back next week with 4 days of virtual Spark NLP training and certification. The workshop will walk you through state-of-the-art NLP using Johnson Labs' open source Spark NLP library, as well as the Spark NLP for Healthcare library. Check out the link in the chat to see details and to register. Once again, many thanks to all of you for joining. We are very proud to be part of this amazing global NLP community. Keep in touch and have a wonderful rest of your day.